This video describes the providing adaptive users interface in deviceless learning environments. We are Mizutani Laboratory, Faculty of Science and Engineering, Keikyo University, Japan. Today, smart devices such as smartphones and tablets have become indispensable in educational settings. Many studies have revealed that the use of these devices enhance the learning motivation and understanding of students. Some countries are beginning to invest more in one-to-one computing. However, about one-to-one computing in educational settings, there are some problems that remain unresolved to date. Initial costs and operational costs are always mentioned as problems. There is a report which mentioned little evidence about the cost effectiveness of smart devices. There is also a report that the greatest challenge for the teachers was that the iPads provided a distraction for the students. Primary and junior high school students often lose, break their device and forget to charge their batteries compared to higher educational students. Furthermore, these studies also attempt to solve a problem which is students' desks being narrow. In most Japanese primary school, a desk is approximately 600mm wide and 400mm long. Because the desks are small, there is insufficient space to put smart devices in addition to teaching materials such as textbooks, notebooks, reference documents, distributed printouts, and stationery on the desk. This makes it difficult to utilize smart devices in conventional classes that require the use of such materials. For these problems, this study considers a method of providing adaptive UI with a size and shape that are adjusted to fit blank spaces on a desk to respond to this problem. Moreover, by improving the problems of one-to-one computing simultaneously, we aim to enable a learning environment where IT can be utilized in conventional classes. This study applies two methods for providing adaptive user interfaces. Firstly, adaptive UIs are provided in deviceless learning environment, which is called followable learning environment. Secondly, to detect blank spaces of a student's desk, a mesh type object detector is applied to the prototype system of a followable learning environment. We previously proposed a deviceless learning environment called the followable learning environment. FLE detects the arrangement of the student's desk and gesture with the use of sensors located on the ceiling and projects user interfaces on each student's desk, using the partial projecting area of a projector placed on the ceiling of the classroom. It is the same techniques as projection-based AR, however, FLE is distinguished by projecting one UI in the partial projecting area of one projector. This is a video of the prototype system of FLE, which uses one sensor and one projector. The prototype system can project UIs for 4 desks at the same time. Moreover, FLE can detect a desk layout and adaptively project UIs with adjusted angles or layout sizes. Hence, FLE can easily provide collaborative environments. On the FLE, because individual devices are not required, the risk of device loss, breakage, and batteries problems are resolved. Furthermore, the architecture of FLE is similar to a thin client system. Since we can easily manage UIs and data, reduction of management costs and improvement to the distraction problem due to the use of smart devices can be expected. To detect blank space on a desk, a mesh type object detector, mesh RCNN, which is a convolutional neural network model, is applied. Each area of an object on a desk, such as textbooks, notebooks, and stationery, are detected by the mesh RCNN model. After detecting objects on a desk, a blank space is calculated as the difference between the area of each object and the areas of a student's desk. Adaptive UI is projected in 3 steps as followed. First, if detected space areas are adjacent, they are combined into a single area. Next, a suitable area for UI projection is selected with consideration to its position, square area, and aspect ratio. Finally, a UI is projected that is adjusted in size and shape adapted to the selected area. This figure shows an example of the result of detected objects and selected area of blank space on the desk. We can see a detected blank space which avoids the areas of textbooks, a notebook, and pens. We implemented these methods on the prototype system of FLE. A model of Inception ResNet version 2 was used as a mesh RCNN model in the system. We can see the system projects an adaptive UI while fitting the detected blank space. These UIs are pseudo UI. In the future, adaptive UI will be implemented in application programs such as learning support, CSCL tools, and so on. As you can see, adaptive UIs are projected to fit size and shape to a blank space on a desk. However, some issues still remain. Since the system uses a high-definition detection model, the detecting process of blank space is slow. It takes approximately 5 seconds. The precision of object detection is also insufficient. In particular, as there are many kinds and shapes of stationery that exist, more sample images are needed to train the model. Resolving these issues is necessary for practical use.